Okay, it looks like a pretty good time to get started. Welcome back to class, everybody. So here's what we did last time. So of course, last time was the exam time, but the one before last time, what we did was we talked a little bit about the exam. We did the practice exam in class, and then we continued with discussing how to solve shortest path in Pyomo, but we didn't quite get through it. So we saw how to do things like define the objective function and get some printouts to make sure that Pyomo is doing what we want it to do, but we didn't get to actually solve the linear program and so forth. So here's the plan for today. I'll spend a little bit of time talking about the exam and maybe going quickly through my solution to it and some common errors that I found on the exams that I graded. We'll talk sometime about the project and the final deliverables for the project and what the plan is for the rest of the semester for that. So the reason I want to do that now is because the last few weeks of class are going to be project presentations, and some of you are going to go first. And because of that, I want to make sure that those people who go first have enough time to actually work on the project and produce something meaningful beforehand. So we're going to spend some time talking about that. Then we're going to finish shortest path in Pyomo, which is going to give you everything that you need to do the next homework assignment. So your current homework assignment on large-scale machine learning is due next Tuesday, and the end of discussion today should set you up for doing the next one. So we'll talk about what that assignment is. And if we get through all that, we're going to do another example optimization problem in Pyomo, which is facility location. But before I jump into today's material, are there any questions in class in general or anything else? Yeah.
Talk about homework 4.
Oh yeah, absolutely. And your questions on homework 4, like I can insert, before we even start. So if you have questions on homework 4, please ask them right now, and we'll start that way.
We talked generally about the multinomial, about the
Okay, so the question is how to calculate the gradient of the multinomial logistic classifier. So let me just open up the description. Oh, that's a new homework assignment. And let's take a look at the actual objective function there. Okay, so this is a discussion of the objective function of the multinomial logistic. So let me just kind of go through these steps first, and then we'll talk about the gradient. So my first question is, do you all understand why this expression here, and I can increase the font in just a second, but do you understand why this expression is a maximum likelihood expression? So yeah, my question was, why is this expression a maximum likelihood expression? So so here's how to think about it. I have a bunch of data, which is my training set, right? And my training set has these vectors and the classes that they're in. And what a multinomial logistic classifier does is it assigns a probability for each class, right? So what's the probability that AK gets its actually true class, right? So AK is the image vector, and its true class is BK, right? And so if you forget all the rest of this notation, this is the probability that the vector AK gets actually its true label assigned to it. And there's a typo here. This should say AK on the bottom, right? Because it's the probability of that class over the sum of the probabilities for all the classes. Make sense? And I'm going to fix that online. But okay, so that's for one data point, right? But if we think of all of the data points as independent, the probability of seeing all of those things happen is this product, right? Because we have a product of independent events. And the thing that we don't know in this expression is the w's, right? Like those are the parameters of our distribution. And so this is a maximum likelihood because it's trying to find the parameters that maximize the probability of seeing the data that you actually are seeing. Does that make sense? Okay, so then let's follow through the rest of the discussion here. And you can see that here I wrote it correctly, right? So it's AK because it's for that particular piece of data, what's the probability of seeing it? Yeah.
So will that last part be from 0 to 1 for every W?
Which one?
The last part with the numerator or the denominator?
This part?
The whole thing after the product.
The whole thing, you mean the denominator?
The numerator and the denominator.
So can you ask your question again? Will that be?
When you evaluate that for a certain W, it'll be between 0 and 1.
Oh, absolutely. Yeah, it's going to be between 0 and 1. And why is that? It's because we have that particular W in the numerator and the sum over all W's in the denominator, right? And each of these is an exponent, and exponents are always positive. So this has to be between 0 and 1. Regardless of what the value of W is, it always has to be between 0 and 1. Not only that, but if somebody gives me an AK, and I sum the probabilities over all classes, what am I going to get? 1, right? Because what's going to happen is the denominator is the sum, and it's going to be the same for all the classes, and I'm going to get the same sum on top, and it's going to cancel, and I get 1, right? So the W's basically specify a probability distribution over the classes given a particular input vector. Make sense? Okay, so now let's go to the rest of this discussion and get to how to actually compute the gradient. Okay, so one of the main issues with solving this directly with our code is that our code does minimization, right? So we're doing stochastic gradient descent, and we've been using it for minimizing things like parabolas and so forth. And this is a maximization, which is not that nice to put into our code. So let's do a few transformations to make it nice so that we can fit it in our code. So the first transformation that we're going to do is just take a log of the objective function, okay? So when we take a log, and what that does is it preserves the order of things. So let me just write that out. And maybe we discussed this a few lectures ago, I don't quite remember. Okay, so log looks like this. Log looks like that, right? And so if I have 2 points here, A and B, so if A is less than B, then this is log A, this is log B. Then log A has to be less than log B, right? It's because log is a constantly increasing function, right? So it's never flat and it never decreases. So that means that if A is less than B, then the log of A has to be less than the log of B, right? So the reason I can take logs in the optimization is if you think of two W's, right? Like one set of W's and another set of W's. If one of them was better before taking logs, that same one is going to be better after taking logs, right? So what's not quite right here is that the objective function values aren't going to be the same, but the order of the W's is going to be the same. So whatever was the maximum W here is going to be the maximum W there. Does that make sense? Okay, so taking logs preserves the order of the W's, so we're going to get the same W as the optimizer. Okay, so that took us here. And then our next problem was that we had a max here, but our code does mins. So one thing that we're going to do is multiply the inner part by a -1 and move a minus across the optimization operator. So when you take a -1 sign and move it across the optimization operator, it changes it from a max to a min. Okay? And now we have a problem here, minimize over W, this stuff, that we can actually stick into our stochastic gradient descent code just fine, right? So now the question is, what gradient do I stick into stochastic gradient descent? So it would be the gradient of this function. Okay. So one of the things that we need for stochastic gradient descent to work correctly is that the function that we're minimizing should be convex. In other words, it should have a unique minimizer, hopefully, right? So what is this function? This first part, what kind of function is it? It's just linear, right? So no problem there. Like, that should work just fine. The second part is something that people often call log sum exp, because it's a log of a sum of exponentials. And it turns out that it's well known that this is convex. So this is a perfectly fine function to stick into stochastic gradient descent to optimize for the W's, right? Okay, so going back to your question, is your question that you'd like us to do some algebra to figure out what the gradient looks like together, or is this explanation sufficient?
I'd like to know the gradient.
Okay, so let's do some algebra to figure it out. So first of all, how many coordinates is the gradient going to have? So, say again? Can you say your number that you said previously? 784. So not quite. So more than that. Yeah, 10 times 784. Okay? Because we have one W for each class, right? And each W has 784 coordinates. And so this entire function is a function in 10 times 784 space. So it takes a vector of length 7,840, and our gradient is going to have 7,840 coordinates to it. Okay? So to figure out so we have to figure out the value for each of those coordinates. Okay? So can you help me do that? So how do I figure out the value? So each of these W's, there's like a W0, a W1, a W2, right? So let me maybe write this and then we can do it together. So I'm just going to try to copy this expression here. So it's minus the sum from I equals 1 to the data set, whatever that data set size was WBK times AK, right? Plus the sum from I equals 1 to whatever the data set size is of log, and here I have the sum from I equals, or maybe J equals 0 to 9 of WJ times AK. So let me make this a K, just to be the same as the write-up. This is an I. I have e to the WI times AK. Is that right? I think I copied it correctly. And so let's think about what our gradient looks like, right? So our gradient, so this is what our input looks like. It's going to be the first coordinate of W0, the second coordinate of W0, the 798th, or what was it, 784 of W0, then W1's first coordinate, and so forth until W9's 784th coordinate. Right, so the total length here is 10 times 784. So that's what the input looks like. And let's figure out the gradient for just one of these. So if we figure out the gradient for one of them, it's pretty much the same for all of them, right? So what's the gradient for W01? Okay. So let's think about, like, where does W01 show up in the first term? Right, so I'm going to take the derivative with respect to W01. In this first term, it's all a bunch of linear stuff. So what's going to get left when I take the derivative with respect to W01 of the first term? Yeah, I'm going to get A1. So let me call it like this. And this is for all k whose label is 0, right? Does that make sense? Because W0 only appears with A's whose label is 0, right? Like if a particular image's label is 1, then it's going to get multiplied by W1. And so when I take the derivative with respect to W01, that's just going to be 0. It's going to entirely go away. So the only thing that's left out of this sum is, out of all of the images whose label is 0, taking their first coordinate, and there's still going to be a negative sign over there, and summing those up and taking a negative. Is that fine? Okay, so now let's figure out what's going to happen with the rest of it. Right, so this is kind of like the slightly easier part. So what happens with the second expression there?
That portion goes in denominator and then...
Right, so we have to use chain rule for computing things. So let's do that. So I get plus. Okay, so let me ask you another question. Does W01, so W01 only appeared on the images that had label 0 over here. Does W01 appear only on the images that have label 0 over there, or no? No, it appears on every image, right? Like on every image, because it's in the sum for every image, right? Okay, so over here we're going to have the sum from k equals 1 to whatever the data set size is. And now we're going to apply the chain rule. So here I have 1 over the sum from I equals 0 to 9 of e to the wi ak, right? So this is just me taking a derivative of the log. And now I have to take a derivative of this, okay? So help me take the derivative of that with respect to W01. What do I get? So I have to do chain rule again, right? So which part of this sum is going to remain and which part is going to like go away? Only the I equal to 0 is going to remain, right? So here I have that part, and all the other parts of the sum got zeroed out. But then I have one more thing over here, which is so not AK but AK1. So why not AK but AK1? What am I taking the derivative with respect to? W01, right? So this is an exponent, and at the top of the exponent is a sum over a bunch of these W's times the A, right? When I take the derivative of that with respect to W01, what's going to be left? Is only the coefficient of W01. Does that make sense? Yeah, that's right. It's the first pixel of the AK. Exactly. Does that make sense? So I think this is right. I suggest double checking it by one, going through the calculus again yourself, and 2, implementing it and see if you actually get the image that I got. Yeah, question.
I was going to ask, on the far right, the e to the W0 AK, does that, so W0 is, I think, has 784 elements.
Yeah.
AK, I think, has 784 elements.
Yep.
So does that evaluate, is that like element-wise, and then there's an implicit sum there?
Yeah, it's a vector dot product. It's exactly coordinate-wise multiplication plus a sum.
Okay.
That's exactly what that means, yeah. So let me give you some intuition about what's going on in this classifier and like why it works and why the coordinates look like this. So this is the gradient for the 4th category for W4, right? And so W4, the gradient there has 784 positions, and I've made them into a picture the exact same way that you made like the images into a picture and plotted it here, right? So whenever I have a pixel that happens mostly in the 4s and not in the other ones, I get this very negative value. So that's from the first part, right? So the first part, what did it do? It summed over all the pixels that were labeled 4s, right? And then there's the second part that's summing over all the images, right? So the pixels that are happening in other places that are not 4s, those are going to get this sort of positive value, right? So what that's doing is if you're getting a pixel on images that don't look like they're 4s, that's going to push down the probability of the 4th category. And if you're getting a pixel that basically only happens on 4s, that's going to push up the probability of the 4 category. Does that make sense? So that's kind of the idea behind these gradients and how that classifier generally works. And you should get very similar pictures if you look at the other categories, right? So if you look at 3s, you're going to get sort of blue area, like negative gradients for pixels that are primarily for 3s, and this sort of more reddish area for pixels that happen in other images that are not 3s. Okay? So one other thing that's interesting here, and when I programmed this assignment, I spent a bit of time thinking about it, is this is reasonably nice for us to write down, but like programming it is significantly more difficult, okay? So I had to spend some time to think about how to make this in vectorized form so that it operates reasonably quickly on the sizes of the data that we have, right? Because if we write a for loop that's iterating 8,000 times over all the W's, it's going to be pretty slow. However, you might try starting that way and then vectorizing, because it gives you a way to debug your code, right? So other questions on homework 4, or anything else on homework 4? Yeah.
Yeah. I had a question. I was wondering if you mentioned using ND image sum, and I tried using that. The place where I thought that would be most useful was when so we're trying to take this sum for, so we have like a 50,000 by 784 array, and we're taking the sum of that minus, like we have our W, and we're subtracting each of the different 1 by 784 arrays, and then we're trying to piece that back together to figure out that's going to be what goes into the classifier and stuff. And I guess I ended up doing something very more rudimentary, where I'm just saying here are the entries of that 1 by 784 array that we have or the entry. Here are the images that are classified with a specific digit, and I made a separate line basically for each of those. Like here's the images that are classified with that digit.
Yeah. So is the question basically what do I use ND image sum for?
I'm asking basically if it's for that. Yeah.
Oh. So I don't.
ND image sum to sum over those.
I don't quite remember exactly where I used it, but a fantastic place to use it is here. in vectorizing this part, for example.
So can you give me, the documentation for ND image sum?
Yeah, so let's go over ND image sum and see what it actually does. And then we can talk about how it would be actually useful to vectorize this first part. That's the sum over all these pixels, right?
Okay, sure.
Because if you think about it, I need sort of the first pixel for all the images that are labeled 1 in the first coordinate, right? And that's like a really complicated like if statements and for loops that are going on in there. But ND image sum can let you do all of that in a single line.
Right,
Okay.
Yeah. I didn't use any for loops to do it, but I did have to basically write a line that pulls out all of the indices associated with any digit.
Yeah, so ND image sum works very similarly. So let me open up IPython. And where exactly was it? I've forgotten.
Above the code that you wrote for k-means classifier, yeah. Right there.
It's an ND image, okay. Okay, so there's three things that are going on that are inputs to this. So one is some input data, the second is some labels, and the last one is an index, which is the sequence of labels of the objects to be measured. Okay, so let's forget the actual verbiage that these people are using, and then let's take a look at an example. So let's say that we have our input data is something like this. Let's just make zeros that's, let's say, 3 by 4, okay? So 3 rows, 4 columns, and let me sort of give some values to some part of it here. So say input data 0, 1 is 5, 0, 3 is 7, 1, 2 is 4, and 2, 3 is 12. Okay, so that's the input data. Okay, so now let's put some labels on it, which is going to look, let's say, the same. It's going to be the same size as the input data.
Okay, so the labels should be the same size.
Okay. That's how I generally use it. And it actually does broadcasting of the label, so that if it's not the same size, it's going to broadcast it out so that it is the same size. Okay. So let's then use scipy.ndImageSum of the input data and these labels. And then I have to specify some outputs, right? So what this is basically saying is the following. Take this input data, take the labels associated with the input data, and give me the sums for each of these labels. So by saying 0 here, I'm saying sum up all of the entries in the input data. And the reason it's all the entries is because every entry has a label of 0.
Okay.
Does that make sense? So when I hit enter here, I get 28, and if I do input data dot sum, I should also get 28.
Right, yeah, that makes sense.
So let's change the labels a little bit. So let's take a look at the input data, and let's take a look at the labels. And let's let labels 0, 1 be equal to 1, and labels 0, 3 be equal to 1, and let's say labels 2, 3 be equal to 1, and labels 1, 2, let's set it equal to 2. Okay, so let's take a look at the input data again, and let's take a look at the labels. Okay, so imagine superimposing these over each other. So what are the entries that correspond to a label of 1? It's the 5, the 7, and the 12, right? what are the entries that correspond to a label of 2? It's the 4. And what are the entries that correspond to a label of 0? It's all the zeros, okay? So now, if I call NDImageSum with 0, 1, and 2, what I'm asking is give me the sum of all the entries that correspond to label 0, the sum of all the entries that correspond to label 1, and the sum of all the entries that correspond to label 2. So for 2, hopefully I should get a 4, and for 1, I should get whatever that is, like 21. Or, yeah. Make sense? And so then how is this useful for doing this part of the gradient?
You can use the data 1 with all the labels for the digits and use that like we're summing everything.
Exactly. So I just give each of the W's a label, right? So I'm going to have 7,840 labels. And I'm going to label each image with wherever that sum is supposed to go, right? So the 0 images are going to get labels between 1 and 784. The 1 images are going to get labels from 785 to whatever, right? And then a single call to NDImageSum is going to compute like all of this for like the whole data set, right? For all 7,000 coordinates.
Okay, so when you said 0, 1, 2, you might have just shown that. It gives a different sum for each of those labels.
Yeah, yeah.
Okay. You might have used a different lemon for this sum anyway. Yeah, okay, I see.
So I asked for 3 labels, and I got 3 sums.
Okay, cool.
So I'm going to ask for 7,000 labels and give 7,000 labels to my data set, and I'm going to get 7,000 sums out that are like all the right pixel for the data set. Does that make sense? Okay, other questions about homework 4 before we talk about the exam? Yeah?
Can you just go high level with the parallel and engine data storage module in script form, or how we should use it? It's a part of
So your question was at a high level, how do you set this up?
Well, you recommend using 2 Python scripts. One is parallel underscore index.py.
Yep.
The other one is engine data store.py.
Yep.
I'm curious how both of those are
Okay, so engine data store is something that's going to get imported at the engines. And that's where you're going to create the data set in each engine. So each engine is going to import engine data store, and inside of it, it's going to import only a fourth or how many, whatever fraction of the total data set you're going to store at that engine. Does that make sense? And then parallel mnist is going to be what gets executed at the client side. Okay, so that's going to be the thing that runs stochastic gradient descent. And stochastic gradient descent is going to use all of those engines to compute gradients over the entire data set. Okay, so another thing I'm going to suggest is the following. We have room in the class schedule to push this assignment due date back by about a week maximum, okay? If you think that you'll learn more by doing that, then I suggest doing that, because there's a lot to learn here that's useful. Certainly parallelization is super, super useful in lots and lots of problems. And also sort of thinking through the various gradients and being able to play around with your code is also something useful. So is that what you all want to do?
Would you also be pushing homework 5 and 6? Or would
Yeah, I'm going to push them back. Yeah. Yes.
Yeah, what's the catch?
The catch is that probably our second exam is going to be like right before the presentation starts. Okay. So there's,
Like the class period before?
yeah, that's right. So we're going to have like a bit more of a compressed timeline, I think, later. Another related comment to that is these are great questions. So thanks very much for asking questions about homework 4, because if you hadn't asked it, I would have assumed that everybody's doing fantastic at it and like continued right along, right? And so with that in mind, spend the weekend trying to do this assignment. and come in with lots of questions on Tuesday, right? And if on Tuesday you all say, oh, you know, things went fantastic, like I could get it to run just fine, then like we can move on with other stuff, okay? So any other questions or comments about the assignment?
One more quick question. What's the negative from the min? Can you switch from min to max?
Yeah, so there are some typos.
That couldn't stand especially, but when you want to make
Yeah, so it's a question of what the equal sign means, okay? So if you look at these two, the actual objective function value is equal. Okay, if I didn't have this negative sign, the objective function values would have the same magnitude but be of opposite signs. And so what makes them equal is the fact that I kept this minus sign here. Over here, the objective function values are not equal, but what's equal is the maximizers. Like, so the argmaxes are the same in both of them. Does that make sense? Okay. So other questions on the homework assignment or anything else? Okay, if not, let's briefly talk about the exam. And so I've graded the exam. This is a distribution of the grades on the exam. So they're not evenly spaced bins here. So the bins are roughly the way that I'm going to assign letter grades. So, you know, this would be an A, 92, and above. This would be an A minus, 90 to 92, and so forth, okay? So several things to say about this, which is that exams make up a very small portion of your overall grade in the course, okay? And so very often, like, you could be down here and on the exams, but still get an A in the course, because a lot of your course grade comes from the homework assignments and from the project. The project basically is equally weighted as the exams, right? So that's one thing to keep in mind. So other comments I have about the exam is that, first, probably about 10% or more of you got hundreds, okay? So in that sense, there's a good fraction of the class that's really understanding things pretty well and doesn't seem to have like too many issues in terms of the material. Some of these grades here are just because of some common mistakes that we can talk about in a minute. So one of the most common mistakes was how to use the chunk size in Pandas Read CSV. So oftentimes what people did was they read in the CSV with chunk size and then immediately used concat on that. So what does that do if I read in things and then use concat immediately? Yeah, it just reads the whole data set in memory, right? Which is the thing that basically doesn't work if I give you a big data set, right? For this assignment, for the exam, I very purposefully gave you a relatively small one because I didn't want your computer to be crashing and for you to be restarting and so forth. But that's also why I put in the comment that I'll be looking for like not reading the whole data set in memory, right? And so a better way to do that is, and we can look at the code that I wrote in a minute, is to basically like scan through the data, like each chunk at a time, right? And each chunk you can sort of build up the histogram that you need, and at the end you're done with reading through the data set and you have the histogram that you need to like plot or compute CDFs or PDFs or what have you, okay? I'd say that's kind of like the main common mistake. Like the other common mistake, it was efficiency. So we had three functions, like one was for plotting a histogram, one was for CDFs, and one was for PDFs. So some folks that read in the data set in this chunk size manner, like did it separately for each function. Whereas you could just do it once at the beginning, store the histogram results, and then just use the histogram to compute the PDFs and the CDFs. Does that make sense? So that's just kind of an efficiency question as opposed to like reading in the data set one chunk at a time. So any questions or comments about the exam before we take a look at a solution relatively quickly? Okay, so let's take a look at at least one solution. And there were many, and yours might be slightly different than mine, and if they were slightly different, they were just as good. So, okay, so this was some code that I used for the first part of the sections, and I just commented it out. So let's just take a look at the class part to see what my code did. So many of you had almost the exact same structure, which kind of shows you that after you think a little bit about programming or you've had some experience programming, you're likely to come up with the same structure as somebody else for the same problem. So here we have the airport name, the file name, and the minutes per bin. And then after that, I'm going to call get frequency, which is going to do this scan through the various chunks of the data. So this is get frequency. It takes in the CSV file with this data reader, right? So now it's not a data frame. It's just something that produces a data frame every time you iterate through it, or with get next chunk or whatever it is with next. I also define the bins, which is going to be sort of how I'm going to be computing my histogram. And then I define the counts for each of those bins. So the counts start out as 0, and whenever I see a particular delay, I'm going to add to the corresponding count. Okay. So oftentimes people call this an aggregator. If you're like scanning through some data set and you want to get some value out, like the mean or something like that, you sort of keep an aggregator that every time you see a piece of data, you're going to add to that. So then I iterate over each of the chunks in the data set, and for this chunk, drop all airports other than the airport I'm looking at. And then I'm going to add to the counts. So what am I going to add to the counts? I'm going to look at all the delays where it didn't get canceled and convert it to numeric, right? So that gets added to the counts. And then to the last count, which is my 24-hour count, I'm going to add all the canceled flights. And then at the end, after I have all the counts, I'm going to compute the frequency, which is just the counts over the sum of the counts. Okay? Then plotting the histogram, I think almost all of you did this the same way that I did, so nothing particularly interesting there. Yeah?
There's some values which are empty in the data set. How is that handled?
So histogram 2 probably just drops nams, which some of you did explicitly by dropping it from the data frame. So then the CDF and this PDF, you just kind of figure out the right index in the frequency and then sum up for the CDF from everything from the beginning to that index. And for this minutes low and minutes high, you sum up between the minimum index and the maximum index, which you get from the two values that were passed in. Okay, and like I said, there are various variations of this that were all good. So many of you that sort of have slight variants of this probably got hundreds. And this is my code for then creating the histograms and plotting them, saving the figures, and then printing out the delays. Okay, so if there's no further questions about that, I'd like to spend a little bit of time talking about the project, which is, in addition to the homework assignment, something that you should all be thinking about. So I've uploaded on the class website a new project handout, Project Deliverables, which you can read yourself also. But let's go through it together right now to get an understanding of what's the rough expectation for the project. So the final deliverables for the project are the following. So first, a 26-minute in-class presentation followed by 4 minutes of questions and discussion. So that means that your team is going to be in front of class presenting what you did for about 30 minutes. And in those 30 minutes, what I'm looking for is that you teach the rest of class something, okay? So think about what is new and different about your project than what we discussed in class, than what maybe other teams are doing. that the people who are listening to you can walk out of lecture that day and think, oh, I learned that from these folks. So that's one of the main things I'm going to be looking for. So other things that are deliverables are the slides for your presentation in PDF format, and a 3-page executive summary of the project and the results in PDF format. So I'm going to post all of these online for you guys to look at afterwards if you want to. And the final thing is the Python program and example data files for your project. So this is essentially everything required to reproduce or rederive and rerun the results in your presentation and summary. Right? So one of the things that I'm going to be looking for is significant complexity in your project. Now that can come up in many, many different ways, and it's going to be different for different teams. So some people are going to have complex modeling. Some people are going to sort of have complex data processing. Some people are going to teach us about new modules, perhaps, that we haven't learned about in class and so forth. So in terms of when things are due, so some of you have to deliver your presentation earlier than others. So maybe as much as 3 or 4 weeks earlier because we have Thanksgiving in between as well, okay? However, the final deliverables are due for everyone on the last day of class. So that's Friday, December 2nd. So that means that if you're one of the first teams that goes and you've worked really hard at it at the beginning and you get some hard questions like after your presentation, you still have some time to make your project better before you actually turn everything in. And that includes like updating your slides or your executive summary or what have you. These are just some instructions on how to name your files. So that's really going to help me in terms of organizing things and putting them online towards the end of class. And let's talk a little bit about the presentation content. So this is going to also help you think about what you should think about as you're doing your project. So this is just a suggestion, of course, but the key to a good presentation is teaching the class something. So identify ahead of time what you want to teach people about so that you can focus your project's complexity on that particular thing. And 30 minutes is a long time, okay? So make sure that you have sort of sufficient material to fit in those 30 minutes. So things that you might include in your presentation is like, what's the problem? So in English, what's the real problem you're analyzing? Why is it important? And what's the basic question you're trying to answer? So if we use your current homework assignment as an example, the problem would be given an image, how do you automatically figure out what number is written on it, right? Why is it important? Well, because we need that all the time for all kinds of different applications, and you could describe that. So how do other people answer this problem? So this is also really important because usually for the problem you're thinking about, somebody else has thought about it before, either in a research paper or they've written some program for it already. And so this is important to give the audience context for your problem, to understand how what you're doing relates to other things that exist. How did you mathematically model the real world? So this would be some explanation, for example, the way that we talked today about maximum likelihood and how that fits into that particular multinomial logistic classifier. Then some analysis design. So what is it that you actually wanted to do? Like, how do you actually design the problems that you're going to solve, right? So maybe something about your program design or what kind of experiments you want to run, so forth. Or things like what are the key experiments or questions answered using your software. And then the analysis results. So tell us something interesting about the problem that you're talking about. So what are the insights that you gained? Teach the audience something about what you discovered, right? So interesting things from earlier today might be the interpretation of the gradient for a multinomial logistic classifier, right? So that's something that doesn't come from the math, but it comes from looking at the results of the program and trying to reinterpret it back into what the math means. And then some summary and conclusion, which is you all have limited time to do this, right? Basically half a semester, if you think about it from now until the end. So here I'd be looking for, if you had 3 additional months, which is a ton of programming time, what are other things that you would do to make your project better? And then finally, for the executive write-up, what I'd like you to focus on is basically the problem, the results, and why the results make sense. So in specific, in your executive write-up, you probably shouldn't be putting like Python code in it, right? Because it should just focus on the actual problem and the analysis that you did, as opposed to the specifics of the code. But you could explain like what's new about your code, right? Like what's interesting about it, what you're doing different than other people, and so forth. And maybe this is sort of the way I think about projects when I'm in the audience and listening to you all towards the end of the semester, which is I'm looking for several qualities, and different groups might be sort of at different places in these qualities, and any of them can make for a fantastic project, right? So not all groups have to be the same in terms of how the project ends up. But things I'll be looking for are meaningful analysis. So like, what kind of insights did you give us about the problem? Like, what did we learn from listening to you about your problem setup and so forth? Innovation and creativity. So what's new that you did that was different than just pulling some software from online and just applying it to a data set, right? So what's the new innovation or the creativity that you're applying to this problem? Technical complexity, this can come into lots of things, like maybe your math model is complicated, maybe your program is complicated, maybe you had to do a lot of interesting data processing to actually get the problem to work. Delivery and presentation and executive summary is basically how you communicate all of those things to the class. Because you might have a fantastic project that's really, really complicated, but if there's sort of a breakdown in communication during the presentation, the audience is still not going to gain anything from it, if that makes sense. Okay? So those are the things that I'd like you to think about over the next few weeks as you work on your projects with your groups. And I'm going to create the presentation schedule like sometime over the next week or two so that people know who's going first and so forth, and you can allocate your time appropriately. Okay? Questions about that or anything else related to that? Okay, if not, I'd like to finish discussing how to use Pyomo to solve shortest path. So very quickly, I just want to remind us where we were. So we had this linear program for shortest path. It had an objective, it had constraints, it had variables, and it had two different sets, which was the set of edges and the set of nodes. And where we were towards the end of our last discussion on this topic was we read through some code to create the sets, we read through some code to create the variables, we created the objective function, and we even printed it out, okay? And where we were was we just got done reading the code that's going to create the constraints, okay? And the main difference between the objective and the constraints was that we have one constraint for each node. And so here we wrote a function that takes not only the model as the first parameter, but also a specific node as the second parameter. Here we computed the predecessors and successors of that node, and we had the sum over all the predecessors of the y's, the sum over the successors of the y's, and that had to equal the node imbalance, right? And then we're saying Pyomo create a constraint that's going to be one for each node in the node set using this function. So what I'd like to do now is spend a little bit of time with the debugger right here so that we can see how all of this works in terms of Pyomo. So I get the division by zero error that I put in there. And that drops me right in this spot in the code. And the first thing I want to do is I want to show you how Pyomo calls this function. Okay? So let's just call flow balance rule with self.m. So self.m because that's my model object, and that's the first thing that's going to get passed in there. And then the second argument is going to be a node name. So I forgot exactly what our node names are. So let's first print self.nodeset. so that we can remember what our node names are. So they're A, B, C, D, and E. So let's print flow balance rule and pass in self.m and the node A. Okay. So what that does is it calls that constraint function for node A, and this is the constraint that got built up for node A. So it was minus A to B, minus A to C, minus A to D, minus A to E equals minus 1. Okay. So why was this? It's because A has only successors out of it, and the node imbalance on A was minus 1, because we wanted to compute the shortest path from A to E, if you all remember. Okay? So similarly, we could call it with B, and now I could take a look to see if Pyomo created the constraint for B correctly. Okay? So this is super useful for debugging your code, because oftentimes to create the constraints you might have lots of complicated if statements and for loops inside the function that actually creates the expression for the constraint. And this lets you sort of debug that on a node by node basis or on a term by term basis. So another thing you could do is take a look at this constraint object, so self.m flow balance, and you could call pretty print on it. So this is Pyomo's built-in method to print out now an entire group of constraints, right? So flow balance was an entire group of constraints, and there's one for each node. So let's read this printout. So the key here is the node for which the constraint corresponds to. So this is the constraint for node A, for node B, C, D, and so forth. And then these constraints have a body, which is the actual expression of all the variables, a lower bound and an upper bound, okay? Because the lower bound and the upper bound are the same, this constraint is basically saying that this expression has to exactly equal minus 1. Similarly here, this expression has to exactly equal 1. If I had only a less than or equal sign, then one of these is going to be a minus infinity or the other is going to be an infinity, okay? And that's how you would see a less than or equal to constraint or a bigger than or equal to constraint. Does that make sense?
Did we create the flow balance thing?
Yeah. So how did I create it? I created it right here. So after defining the flow balance rule function, which creates the expression for each node, right here I'm saying Pyomo create a flow balance constraint, and in it I passed in the set of nodes. So what I'm telling Pyomo here is run a for loop, iterating over these nodes, calling this function for each one of them to build these constraints. Does that make sense? Okay, so let's see. So now we're done with the model because we've specified an objective function, we've specified some constraints, but we haven't solved it. And if you recall, Pyomo isn't a solver. Like it's not going to actually solve a linear program. All it does is it builds it and then passes it to a solver. So let's see how we can use Pyomo to pass things to a solver. So the way that you do that is from Pyomo.opt, you use this solver factory class to instantiate a solver, right? So here I'm saying use Cplex as the solver, but I could have passed in lots of other things. So here I could have passed in Gurobi, I could have passed in GLPK. And one thing that is useful for you all to do before the next assignment is out, whenever that is you might think about installing Cplex or Gurobi on your machines. So both of them are available for free for academics. You can just look at online and figure out how to do it by talking to your classmates. Okay, so here I've instantiated a Cplex solver. And then in the next line, I'm actually telling Cplex to solve the Pyomo model that I've created. So I'm saying Cplex, solve this model. And the way that Pyomo talks to the solver is by writing some files to disk. Those files describe the problem. They also give the solver various parameters and so forth. So right here, I'm saying keep the files that you write to disk because I want to maybe take a look at them to make sure that I'm communicating correctly with the solver. I'm saying also output the solver solution information to the screen. And here I'm passing a bunch of parameters to the solver. Okay, so solvers have all kinds of parameters that tell them what algorithm to use for a linear program, how tolerant the solution has to be, like what should be the optimality gap between the lower and upper bounds, what should be the MIP tolerances if you're solving a mixed integer linear program, and so forth. So this is some options that I'm passing into Cplex. And after this call, the results basically are in here, inside this results object. So the next few lines, just check if the solver completed correctly, because maybe when Pyomo called the solver, like we got some kind of error. So here, it's just checking, is the solver status not okay? And if it's not okay, then it prints out a warning. The solver is not okay. And if the solver's termination condition is not optimal, then maybe this problem was not feasible, for example. Like I set up the constraints in such a way so that there was no solution. So I'm printing out here something that just says that check the solver if it's actually optimal. And in my if name equals main, I just call shortest path with this set of nodes and this set of arcs. So what that's going to do is read in all the data, create the model, and when we call create model, inside of here, we're actually solving it. So if I was doing some more complicated problem, I might want to split the creation and the solve into two different functions, so that maybe I explicitly call solve after I've created it. But let's actually run things to see what happens. And let's take a look at some of the output here. Okay, so the output is what's got printed to the screen because I said t equals true. So this is the output that Cplex is printing when it gets started. So welcome to Cplex and so forth. And over here, it's printing out the various parameters that I passed into it. So for example, the integrality tolerance and the mixed integer optimality gap tolerance and so forth. And over here, you're also getting printouts of where are the files that Pyomo used to communicate with Cplex, okay? So I could go and take a look at this LP file, and maybe we'll do that in just a moment. Maybe let's do that right now. Say again?
Where does Pyomo look for the Cplex interface file?
It's in the, so there's a Cplex executable, and it's going to look at it in the path. Here, if I type, yeah, it's in my actual path. So
I'll have to add the path of the installation.
That's right. That's right. That's right. Okay. And then, so Cplex over here is printing out some information about the problem, how long it took it to read in the problem, how many variables and objectives it has, and then over here, some information about the solution time. So how much pre-solve took, what the objective is, and so forth. So we got the optimal objective is 4. So an interesting thing here is how does the objective, or after Cplex has solved the problem, how do you access all of the parts of the solution in Python again? So they're all stored in that Pyomo model object that we created. So let's take a look at Pyomo model.y, and let's .pprint it. So let me run this again. So running the Pyomo example. And then let's look at the model.y.pprint. So let's remember what I'm accessing here. So this is my object, the shortest path object. On it, it has a Pyomo model, which has a variable y, and I want to print that variable y. And so these are all the y's and their values. So y from A to B is 1, y from B to C is 1, from C to D is 1, and from D to E is 1. So that's going to actually define the shortest path for this shortest path problem. Okay. You can also pretty print the whole model object. Okay, so let's see what happens if I pretty print the whole model object. It's going to print out all the sets I defined. So this is my arc set, my node set. It's going to print out all the variables I defined. So these are my y's. So each y is associated with a key. So this is the y for AB, the y for AC, and so forth. It's going to print out the objective that I defined, which is to minimize this expression of the y's. And it's going to print out the various constraints that I defined, which was a flow balance constraints with these keys, these expressions, and these lower and upper bounds. Yeah?
Why does the objective have active?
Okay, because oftentimes when I'm solving a problem, I might want different objectives. So sometimes I might want this, and sometimes I might want that. And so Pyomo has, you can add two objectives, turn one off, optimize this one, turn this one off, turn this one on, optimize this other one. So other useful things is so what if I want to actually access the value of one of these y's? So I can actually specify a particular y that I want, like the y for AB. And then do dot value, and that allows me to pull out the value of that variable. And now you can go and use that in whatever way that you're going to be visualizing these results, or whatever other like post-processing you're going to do after you actually do the solve. So this is a huge, huge advantage of Pyomo versus other systems. So before Pyomo, there were things like GAMS and AMPL and so forth, but those weren't programming languages. And so it was generally very difficult to sort of write some program to pre-process the data beforehand, then solve, and then write some more program to post-process the data afterwards. But here, because it gives you easy access to the various values, it gives you access to all the Python modules and so forth, it's relatively easy to sort of write these pre-processing and post-processing pieces of code. Okay, so other questions or questions about Pyomo in general? So a key thing, so how many of you are in operations research here? So like maybe about half of you. So for those of you that are here, writing an integer program and solving it is an absolutely key skill required for an OR person, okay? And one of the things that I basically expect you all to be able to do by the time this class is over is if I give you an integer program written on a piece of paper and some data for it, for you to be able to implement that in Pyomo within an hour, okay? So we're going to practice using Pyomo to implement integer programs several times, both in lecture, and that may even be your next exam, okay? Because that's an absolutely like key skill to have. And so in that direction, I'd like to spend a little bit of time discussing another integer program that we're going to write next as an example. So to do that, I just kind of want to set up what the problem is. So the problem is generally called facility location. So here's the basic idea. So I have some network. So each of these points is a node. And I have some distances between these nodes. So maybe there's 10 here, 5 here, 3 here, and so forth. So I have various distances. And each node has, let's say to start, we're going to say each node just has one customer on it. Okay, so think of these customers as maybe people who want to shop at Walmart, okay? And we're Walmart, and we want to figure out where we should put our store in this network. So how would you think about, like if you were Walmart, which node you should put your store in? So which node would you pick? Or how would you decide if one node is better for your store than a different node?
New category, accessibility to...
Yeah, so accessibility is a great thing to do. And if you notice, most Walmart stores are next to a highway, right? Why is that? Because it's easy to get there. So accessibility here is going to be something in terms of the distances, right? So so what we want is accessibility, which is kind of minimize the distance customers have to travel to their nearest store. Right? So if I had two stores, I want to put them in such a way so that each customer sort of gets to pick the closest one, and I'm minimizing the distances that all customers travel to the nearest store. So besides accessibility, another thing that might be an issue is sort of construction costs. And sometimes people call these opening costs. So maybe it costs $100,000 for me to buy a plot of land here, but it only costs $5,000 for me to buy one over there. And so I need to somehow take that into account when I'm selecting my location. Okay? So let's take a look at a specific data set and then try to write down an integer program that's going to help us pick like which locations we're going to put things in. So so I've created a small example data set here. Okay, so here I have some opening costs. So I have 5 nodes, and N1 is relatively cheap compared to N2, N3, N4, and N5. Okay. And then I also have some distances, like N1 to N2 is 10, N1 to N3 is 10, N1 to N4 is 10. Over here we also, I guess, have a N1 to N5. It's also 10. And then 2 is connected to 3, 2 is connected to 4, 3 is connected to 4, and 5 is connected just to 5. Say again? And that may be a typo. So maybe we can change this data. Let's say that, yeah, maybe N4 is connected to N5 with a distance of 10. Okay, so let's draw this network out a little bit. So I have N1, N2, 3, 4, and 5. And N1 was connected to all of them. N2 was connected to 3 and 4. And 3 was connected to 4, and 4 was connected to 5. Okay. So that's what our graph looks like, and each of these are 10s. Okay, so help me try to construct a integer program to decide where to open a Walmart store. Okay, so what are the pieces of an integer program? I need some sets, I need some variables, I need an objective function, and I need some constraints, right? So I need some sets, some variables, an objective, and some constraints. Okay, so what are the sets here? Yeah, so maybe some nodes. Yeah, maybe arcs. Okay, so what variables should we have?
Which should be either you can have either.
So suggestions? Yeah, so I need one variable that tells me, am I going to open a store in this location or not? Right, so I'm going to have something like, let's call it yi, that's 0, 1, which is, do I open a store at node I, right? What other variables might I want?
The odds, the distance, for the distance, since you want to minimize.
Yeah, so how about something like xij, which is, or let me write it like this, xji, which is, does a customer at location j go to a store at location I? Does that make sense? Because I need to know where these customers are going to be able to figure out what the distances are that they're traveling, to be able to express my objective function and so forth. Okay? So this is sort of the start of creating an integer program. And next time we'll go through the rest of the reasoning by writing down an objective function and constraints, and then we'll try to program all that in Python to get a solution to our example. Okay? So thanks a lot for listening, and I'll see you all next week.